Right. So good morning, everyone. It's an absolute delight to present today. Um, I have been a SSPC PI not too long back because I only started in UL as an assistant professor lately. Um, so thanks so much again for offering me this opportunity to SSPC for explaining how one particular group of chemicals that mankind made a like we made has left us at the mercy of, let's say, a brewing ecostorm, right? And literally and figuratively, we are actually staring down the barrel of environmental ruins here. Okay, so before we go to the nitty-gritties, getting on with the science, let's say, I would like to introduce my team here and acknowledge. So I'm living my dream in a way of contributing to academia. And this all started when I moved out of my hometown, Calcutta, back in 2011 to pursue higher education in chemistry. And over the years, almost a decade now, thanks to a number of grants I could win from different public organizations, spread across India, Ireland, and Germany, to be very specific, I started my own research program at UL from September 22. As you can see in the screen, this is my team, two PhD students, Asif and Bhavna, and there are a couple of interns, especially Hannah and Freddie, who have worked with us over the past year. So my group's research interest, in a nutshell, specifically lies in the interface of supramolecular chemistry and porous materials chemistry. And we're a small team of 3 PhD students. It's a growing team, a handful of undergrad interns, and so on. Okay. And they all have the misfortune of pretty much having me as their mentor. All right, so slide 3, which is where things begin in terms of PFAS. Before we go to PFAS, let's rewind the clock to this Greek mythology for a minute. Some of us might recall this from our history lessons. So this particular artwork still now is a showpiece in the Musée Antoine Vivenel. Pardon my pronunciation there, but anyway. So this is still in the city of Compiègne in northern France. And this artwork, what it depicts is the father Daedalus and his son Icarus. And what Daedalus did here in this case was he said, it stands for, this painting kind of still stands for as a symbol of wisdom and knowledge, because Daedalus was the skillful architect and craftsman from Crete, and he created wings from feathers and wax. He warned his son Icarus not to fly too close to the sun, causing, and Icarus did, of course, as you see, Icarus falling. So what happened was, the beeswax in his wings melt. So Icarus fell from the sky, plunged into the sea, and drowned. So this myth gave rise to the expression, don't fly too close to the sun, right? So this actually kind of sets us today in a good bit of way as a timeless reminder of the need for caution. We can't really afford to throw caution to the wind, and because perhaps in our pursuit of our innovations, there's a big need for exercise caution, respect, and humility. As we see today, this is where we stand at the moment. So because we didn't like Icarus, we didn't perhaps listen to all the good things we could have or should have. All right, so let's look at what PFAS has caused. Okay, before I begin, get into the chemistry sides of things. So there's a good reason why this group of anthropogenic chemicals, what do I mean by anthropogenic? I mean man-made chemicals, are rather infamous as forever chemicals. As the slide title says, they are actually known as forever chemicals. Why? Because they have the trifecta. They're pervasive, they're persistent, and they're exceptionally perilous. Okay. And that scores a trifecta. And this is a few of the, if you Google it yourself, there'll be an abundance of disquieting news articles from actually 3 of them on your screen are from the last week. So I didn't have to search back in time. This is in real time because EPA just set a limit for forever chemicals for the first time in the States. So what this tells us is that synthetics that were created in the 20th century, in the middle of 20th century to be more specific, have indeed become an evolutionary force of a kind. And this will have ramifications in terms of altering the human biology and pretty much the wave of life in essence. And if we go through today's whole thing, perhaps we will realize that how the presence of this PFAS alone can shape how we see ourselves in the future, how humankind kind of reproduces itself into our young generations, and even whether subsequent generations might be susceptible to diseases such as certain type of cancers and become resilient against diseases as well. So implications are very disturbing, and that might be just an understatement there. Anyway, right? So I want to go to the next slide. Yeah, okay. Right. So this slide gives away in terms explains why the trace presence of PFAS should be extremely concerning. As you see on your screen, I mean, I just explained that PFAS actually never breaks down. It never goes away. It actually bioaccumulates over prolonged duration. And I mean, they are present in trace quantities in the fresh water that we consume. And it is highly carcinogenic. So what it means is, alarmingly, it plays havoc on men and women both, especially on women's reproductive system, for example. It has been proven that they indeed have a lot of issues to cause. The health detriments are manifold, as the screen reveals here. They can cause, to name a few, they can cause hepatotoxicity, tumor induction, developmental toxicity, and endocrine disruption, all these, and of course, several forms of cancer. During COVID, importantly, they were proved to have a reduced response to vaccines. So this is sort of profoundly threatens our immune system, even if the presence of trace quantity is there, but that trace that is less than 10,000 ppm or so doesn't really save anything because they all kind of checks into our body but never check out. So that means this is going to have prolonged bioaccumulation. So it is in our bodies and our children are born with it. So we have come to a point that where we are knowingly passing the baton to future generations, right? Okay, that's quite scary, I suppose. Now, where are the sources? Where are these chemicals coming from? So these are abundant in firefighting foams. It's also abbreviated as AFFS. So you see the bottom of your screen where you see those firefighting foams there, they're all laden with these PFAS chemicals. You have these non-stick metal cookware, convenience cookware, Teflon. We all use them for frying our omelets, paper food packaging. So all these kind of surface that we all use every day-to-day basis, they all have PFAS in them. They are prevalent contaminants right now in the water resources. And this is, by the way, including the Western world's 100%, because as we will see today, the numbers have spiked to staggering levels in Europe and in the States, including rivers, lakes, and groundwater, of course, affecting both drinking water and aquatic ecosystems, right? So long story short, I mean, right from their discovery to prep the most highly resistant, let's say, coolants. So this is where it started. They were meant to deliver coolants for the Manhattan Project. Actually, we will see go there in a few slides. But fluorocarbons matured, developed quickly from lab chemicals into mass-produced chemicals, mass-produced materials in a matter of years, and then it took a few decades to perfect it. So they are pretty much the silent enablers of the greatest technological achievements that we are making in a way, because not just the atomic bomb, but also Teflon is the stuff of everyday go-to devices, including medical devices, including space flight, cookwares, and everything. Anyway, so that's a good bit of intro into the sources. Now, I probably don't need to explain you all how complex the use of PFAS chemicals is to biopharma chem, because I'm not an expert in biopharma chem, I suppose, very modestly, but there is a definitely need for the biopharma sector to transition into a PFAS-free future. And why I say that with much confidence is that mismatches and conflicts that is rampant, that is there right now across the European regulatory framework. That is, I mean, the ECHA, the European Chemicals Agency, and the EMA, makes for a complex landscape, right, within the biopharma sector, biopharma chem sector. And that actually means that figuring out how to ensure compliance with this European Medicines Agency and the European Chemical Safety Guidelines is gonna be tough, because this is a landscape which is very hard right now to navigate. But as you see here on the screen, this was introduced by EPA, and this tells you the gaskets, the tubes, the line piping, fittings, everywhere, they are all there. All the chromatography equipment that's needed, that essential prerequisites for purifying, the mechanical fittings, everything, everywhere you see, all those process design are still relying upon the use of PFAS. So what I'm trying to say is PFAS-related gaskets, Seppendorfs, and all these plastics, they are ripping off. We somehow need to rip off those existing processes, right? And validate new things. But this is going to be a massive scale task, a gigantic task in some way. But we must do this transition, perhaps no later. Because if we step back long term, we need to transition to more sustainable processes entirely excluding PFAS, right? I mean, if we just took cognizance of the numbers, of the staggering numbers we saw just a couple of slides back there, it's not an option anymore. So not retrofitting an existing process to become more sustainable, to become more carbon neutral and responsibly recycled. The goal is, the mission and the vision should be perhaps to move into inherently sustainable processes that ensure the health of generations to come. So in essence, the future has to be PFAS free. Let's move on to the next slide. Right. So from soil to sea, how does this PFAS kind of, cycles? These chemicals are in air, can be in air if burnt. So they have their own cycles by which they come and go into our body. They don't actually leave the body. So basically what we are talking about by this PFAS cycle is, how are they produced? And then how do they bioaccumulate into various organisms, so there's a complex scheme of primary, secondary, and us as one of the top chain of the food cycle. We will have it at the very fag end of it. But if you notice the right side of your screen, you will see that from the production sector of how raw materials extraction leads to the PFAS production, it actually goes on to have emissions into air, soil, and water. So the exposure can be all three, by all three means. So you can have the workers, consumers, all of us pretty much consume it unknowingly. And this is why all of us have PFAS in our blood. In US, for example, there is already a study that was done, a massive one, which revealed that more than 99% of the population has PFAS. In a concentration that's far above the regulated value at the moment for PFOA. Right. So as we now finally have to go to the chemistry bits, so I will try to not be too much chemistry heavy in today's talk, but let's see how things are in terms of what are PFAS. I'm using this term without perhaps actually explaining the abbreviation. They stand for per and polyfluoroalkylated substances, right? And as you see on the screen now, they can be two types. One is the PFAS polymers on the top, and then the non-polymers, that's the monomers, right? So the PFAS polymers are actually what are touted as the safe versions of PFAS, including your Teflon cookwares, right? So Teflon, which is commercial polymer, is a PFAS polymer because it is safe to have Teflon actually, but the thing gets out of control because PFAS polymers can degrade and lead to these side chains that you see on the screen. Those side chains, if they cleave, those bonds from the surface gets cleaved, then they generate your PFAS monomers, which means it could be the legacy PFAS monomers such as perfluorocarboxylic acids or perfluorosulfonic acid. So what do you have here? You have 8-carbon alkyl chain, which is a long tail hydrocarbon alkyl chain, and you have a carboxylic acid unit, or you may have a sulfonic acid unit, or you may have a alcohol unit. That means it might be an ether as well. But all in all, what you have here is these non-polymers can be the degraded version of the polymers, and they can cause havoc. So this is a cyclic process, of course. Precursors to polymers, so these are the feedstock chemicals that is used to make Teflons. And now Teflons can degrade and lead those monomers to bioaccumulate in our bodies. Right. And this is exactly what is schematically shown here in this slide. If you notice this slide, the middle part of the slide, it tells you how this polymer backbone still remains, but thanks to the cleavage, the bond cleavage, we'll see the new non-polymer PFAS, the length of chain, of course, can vary. So this is an example of a short PFAS chain getting cleaved. But you can ask somebody, a person can definitely have this question like, why does it show these spectacular properties? Why wouldn't I just chase after something else but PFAS? They are kind of, I don't know, the super chemicals, what you can say, because the reason being, look at what they have in them. They are replete with carbon-fluorine bonds. What are carbon-fluorine bonds? Those of us who are having an unfortunate, tryst with our organic chemistry lessons or physical chemistry lessons at some point in our career will remember this bond energy right there in the screen, right? It's the strongest binding energy, bond and strength that an organic bond can offer you. The bond energy for a carbon-fluorine bond is 485 kilojoule per moles, which is the strongest organic bond that exists. So this means if I have those many of carbon fluorines in my chemicals, you can imagine how strong will that entity become. And this means a carbon fluorine, by the way, also has super low surface energy. So this leads to super high hydrophobicity. So now that will directly impact the surface coating property. So this means this is why they are so resistant to water and to any other chemical. Right. So the shorter chain means compared to, so there's a rampant exercise right now going on to move away from the existing regulations on the C8. We'll see that in a few slides from now. But the new practice is to go to shorter chain PFAS, like the ones you see here. The shorter chain means this tail can be shorter, and that way you can somehow dodge the regulation bullets, right? And this is what we generally, the companies which produce them have proven to be very good at, to somehow dodge the immediate regulation and to come up with a new alternative PFAS. But the shorter chain, bear in mind, means that compared to the polymers, they are more mobile. The shorter chains are more mobile PFAS. They are more reactive as well and can be more easily transferred into wildlife and human beings, right? So in fluoropolymers like Teflons, the unit that repeats over and over is, in essence, a simple fluorine atoms attached, like your PTFE fluoropolymers, right? So all in all, that kind of an approach perhaps is not going to solve what we have at the moment. Okay, let's take a step back and let's look at these monomers and the definition of PFAS, which is a matter of conjecture to this date. It is still evolving. The definition is an evolving scenario at the moment, but it's kind of interesting that something that started in the Manhattan Project, as I said, it took us more than 50 years to come up with a definition. So look at that, 2011, that's the first time a PFAS definition came to the fore in 2011, when Robert Buck from DuPont, who was working on a project commissioned by 3M. Anyway, so Robert Buck came up with this simple definition where he said that, CnF2n+1 would be the representative formula of any PFAS. But this doesn't really include everything, you see, because why? Because this means you are going to leave out a lot of things, such as, if you now notice at the pyramid of PFAS chemicals we have right now, these are the ones that got the early attention, the PFOS and the PFOA. Right now, they're restricted chemicals in EU. Now, focus has shifted to the shorter chain alternatives, which are highlighted in the screen by the amber. And if you see the ones in yellow, those are the legacy PFAS, which are most abundant, by the way, in water at the moment, thanks to the decade-long production of those. So right now, the updated definition from 2021 is from OECD and the US Environmental Protection Agency. And this is where we stand. How this has evolved? This has evolved from 400 chemicals, which was covered by Robert Buck's definition, to more than 9,000 chemicals. At this moment, we have actually more than 9,600 chemicals. You can label them as PFAS. And the most infamous at this moment is Genex, Adona, PFBS, and the hexane sulfonic acid and the fluorononanoic acid. These four, and including Adona, there are 5 actually. And just as we speak, there has been a regulation from EPA last week. We will go there in a few slides from now. But I just want to give you a quick rundown into how this definition evolved from about 200 to 300 PFASs when there was the first attempt of harmonizing communication by Robert Buck. So I think my ad-libbing made sure I already covered this in this slide. So what I meant is, before Robert Buck, we had these conflicting jargons. They were not uniform. So now, thanks to this introduction of definition, Buck covered these chemicals as PFAS. What is common in them? They all have either CF2 groups or CF3 groups, so pretty much which falls under the remit of this particular formula, prototype formula. And then we moved on to the next set of much more inclusive definitions set out by OECD and EPA, because of course it was much easier for production companies to dodge the regulations with Buck's definition in place. So now, initially it was a definition in 2018 that was in place, which covered 4,730 PFAS chemicals, and now it is much more than 9,600. This is where we stand in terms of definition. So this is the technical version of the definition at this point in time. And you can ask again, what is not a PFAS then? It appears as we go along this chemical formulas that everything that has a carbon-fluorine bond might be called a PFAS. Not exactly. Why? Because these are the examples. If you see any of these, they don't fit the definition of that OECD and EPA has put out there. The reason being, they don't have those. First of all, there's a caveat to the definition here that your carbon, bromine, carbon, chlorine, if they are connected to the methylene bond, they're not PFAS. You see these carbon, bromine, or any other halogen atoms, but fluorine, when they're connected to the carbon, you cannot call them as PFAS. And the other one is if you have a phenyl and then you have a fluorinated phenyl ring, that doesn't actually allow us to call it as a PFAS chemical, right? So there has to be a methylene or a methyl group, like you see on the top left of your screen, which has to have a carbon-fluorine bond. Okay, that's quite a lot of technicalities, I suppose, but yeah, that is it. Now, this is where perhaps we could all relate to the urgency of the situation. Why does it matter now? And we cannot afford to wait any further, perhaps. So let's look at this case. There's a case study. I'm going to cover one for the US, and the next slide will be dedicated to the Europe landscape. So this is generally when we talk about water pollution, we talk about the developing world. But this is very much a developed nation's problem, because this lady right there with their grandkids, 1-4 and 1-6 at this time, this is in 2016, Hoosick Falls, New York. Those residents filed a large class action lawsuit against the company Saint-Gobain. It fell Saint-Gobain, 3M, and Honeywell, actually, all three of them. And this lawsuit eventually led to a $65 million US dollar settlement for damages and long-term medical monitoring for about 1,800 residents, if I remember correctly the numbers. So that many property owners and residents claimed for it, and Saint-Gobain had to pay up. They had agreed to pay up the 45 million USD, and they did. And last year, in 2023, this lady right there, I think Lorraine is a lifelong resident of Hoosick Falls and a plaintiff in this lawsuit. And she won the case against this company. And why it all started? Because when she was 35, she had breast cancer. And not only her, even if she moved out, her grandkids, as you see in this place, these two little munchkins have PFAS levels of 142 and 117. You can ask, what are these numbers? What do these integers tell us? They actually show us what their blood PFOA levels are in terms of parts per billion. Let me tell you what should be the numbers. So right now, based on the last week legislations that were put out by the EPA, it should be 6 parts per trillion, okay? Or 4 parts per trillion, that low we are talking. Now, these two little ones have 142 and 117, even though they didn't actually live in those places. So clearly their bloodstream came along, they inherited the problem, because Hackett, this lady Lauren Hackett, she showed 266. Her numbers right now stand at 266. By right now, I meant 2016, during which the case was underway. So the irony, by the way, after all of that, after all the rollout, is that Saint-Gobain sponsored New York City's Climate Week in 2023, last year. So this is kind of sort of mimics a rat sponsoring a city sanitation. But anyway, let's move on to the next slide, which is, this is where things could be really alarming for those of us, especially who lives in Europe, because for this particular case, this was, one moment, I'm still struggling with my screen here. Just a tiny bit. Yeah, okay, perfect. Right, so this look at those, look at the green headline over there. There are 2 numbers that you see. What does it tell you? It shows you a microgram per liter of PFOS that was recorded in 2021. This is in the Bloomberg report that's down in your screen at the bottom. So this is the most amount of PFAS ever recorded in the Western countries. And because, again, the safety level is 15 parts per trillion, let me tell you this unit conversion just to keep us all in the same page. So 1 microgram per liter stands for 1,000 parts per trillion, okay? Now, if that is the unit conversion, I have 15 parts per trillion corresponding to 0.015 microgram per liter. That's the safety level of my EPA regulation out last week. Look at that number over there, 257,000 microgram per liter was detected at the Flemish region of Belgium, Antwerp. And this is why there are so many workers right now who are still having health issues, including multiple types of cancer. And you can see the site has been closed sine die. And yeah, I mean, it's terrible, but it's not easy to come out of this mess. Because let me paraphrase it in a way, because the situation here spells a dire emergency for public health, because 3M has been, it has already paid like $850 million US, by the way, in 2018 to settle, without, let's say, admitting the wrongdoing. But in this case, it's clearly yeah, off the chart. Anyway, so that's that. You can see how this site looks like right now, and it doesn't look good, does it? Right. So now that we understand the scale of this problem, removing PFAS from the environment at the rate we are emitting right now would cost more than the global GDP. Just process that information for a minute. It would cost us to mitigate this issue more than the current global GDP. Thus, remediation alone cannot really manage the global PFAS stocks. As you can see in this study from Norway, today these fluorocarbons persist as legacy chemicals prevalent in water systems, serving hundreds of millions of people around the world. So extreme is the the scale is so escalated at the moment that science has yet to determine an environmental half-life. I mean, by that I mean the point at which environmental load would otherwise have. So these 3M and all this, what I discovered, goes on to tell you, where are we there? Look at those numbers at the top. This 84 billion per annum has been determined as the health costs. And then we have more than 100,000 sites across Europe identified to cause PFAS pollution. And then you have these classic law action, as a class action lawsuits. Especially 3M and DuPont has paid a lot of money, and it is just going to spiral more because there are several waiting for the decisions. Now, I know I have been sounding alarm bells for a while, but if you want to pay more attention into the fine print of the problem, I suggest you to go ahead and have a Netflix watch at this piece, Dark Waters. It was none other than the Hulk, Mark Ruffalo, who he did to take a Hulk to come out of the closet and spell out the numbers. And also it was covered pretty well in a humorous way by John Oliver in Last Week Tonight at some point. But so those are your anybody, even a lay person would understand perhaps going by these two. What is the scale? And by the way, the Dark Waters was based on a real situation which Rob Billett ran into, because even after 50 years since DuPont discovered the concentrations here in this factory in the States, it took Rob his federal suit against DuPont after 20 years of it being globally. It was such a long fight for him to get justice. But of course, there is no justice to lost lives. Anyway, so they are extremely mobile, as you see in this number of hotspots and how they have spread across Europe. And right now, if you see all these numbers, I'm not going to read all of them for you because I'm sure you can read them all yourself. But long story short, you can see that there is no way this is going to be addressed just as a quick fix. There is no quick fix to this. The processes have to be rigid, bottom up. We can't really just make small tweaks, and things will not work out that way. The global societal costs, including remediation of PFAS, was just determined last year for the first time in a way in an all-inclusive manner from an agency in Norway. And this amount is staggering. Look, $17 trillion USD. And as I just mentioned a couple of slides back, this is the substitution PFAS practices that are so rampant at this moment. You have shorter chain PFAS replacing the longer chain PFAS, and this is how the manufacturing giants can evade the existing regulations. Well, that actually hopefully could be regulated. There is always a hope to all the loom and gloom, and this is the hope which came into existence last week, because April 10, 2024 was the first time the US EPA introduced 6 specific PFAS-based maximum contaminant levels for these 2 in particular, which are the most infamous, the most legacy PFAS, which is 4 parts per trillion. And for the 4 other replacement PFAS, as I showed you a couple of slides back, those 4, right now the MCLs are set at 10 parts per trillion. The EU guidelines are just about to change in a few weeks or months' time, because as you see right now in Europe, we have this number in place, which is much higher than the EPA. So you see how numbers are not harmonized within the states and the Europe at all, because just last slide we had 4 and 10 parts per trillion. In Europe right now we have much higher tolerance levels. So that's no good, I suppose, in terms of saving us. So just when we try to navigate these numbers, bear in mind this is an evolving landscape, and this might be worse potentially. Okay, now how did it all begin? I'd like to give you I say it a couple of times. I know that it all began in the Manhattan Project, right? So let's look at that for a second. So it all began around 1945 during the Trinity test of the atomic bomb, when it was the fluorochemicals that were needed to quench the uranyl that Oppenheimer's team was dealing with. They needed something that a chemical, potentially a coolant, good coolant that could do the job. And DuPont at that time, actually that was 3M that time, they came up with this solution. So let me just give you, just give me a second. Yeah, right. So before the animation, yes, exactly. So let's, if we set the dial to the past for a while, this Manhattan Project, this is literally the picture from the Trinity test. The mushroom cloud that you saw here from July 1945 was the first detonation of a nuclear weapon, right? So this is very historic, and it's kind of intrinsically linked, or rather inextrinsically, it's somehow very much linked to the PFAS problem we have right now. Because to make this bomb, Oppenheimer and his crew needed a way to enrich the uranium-235, that isotope, using highly corrosive UF6 gas. And how did they go about it? They used fluorine gas for this purpose. The scientists soon enough discovered that the fluorine kind of bonds with carbon molecules to make fluorochemicals, and that's how fluorochemicals first came in. The most highly resistant coolants known to this date are these kind of PFAS-driven polymer or PFAS-driven, such as those, but not exactly Teflon, but similar, compositionally speaking. So this is where it all began. And this critical development indeed led us to the success of Trinity and the Manhattan Project and so on. So this perfected that white powder, right, at that point in time. And as things moved on, the military has used PFAS in firefighting foams to extinguish, even like super hot petroleum-based fires since that time. So if you do a math of how much PFAS gets released into the environment every time there's a firefighting exercise, if there were 500 bases, let's say, participating in a monthly firefighting foam drills, that happen pretty often, by the way, since 1970s until 2020s, where we stand, that might be 500 bases times 12 months times 50 years and times that much PFAS releasing, so which comes to about 300,000 separate environmental catastrophes, right? Yes, those are the zeros we are having, 300,000. So some bases held fire training exercises weekly or bi-weekly, right? So damage is just incalculable. You cannot put a number to it. It is with us forever. Once it's released, it is with us. Now, let's go back to the Teflon, because I'm sure most of us use it on a day-to-day basis. Is it safe? Is it unsafe? Why is it sold, even though it is not really safe? Well, there cannot be a blanket answer to it, but I will just show you what we have here. And also there is a chronology in this slide you can walk yourself through. So Roy Plunkett was the guy at DuPont that time. I said a couple of minutes back, I said that somebody from DuPont discovered it. So this was Roy. And he has been in the Hall of Fame right now, because as one of the most prolific polymer inventions, thanks to this particular discovery. So anyway, so he discovered, as a serendipitous discovery, actually, PTFE first time kicked in, and then he just passed it on to the director, Leslie Groups. And then it was just integrated into the Manhattan Project and moved on. And the first Teflon products were sold commercially under the trademark Teflon starting 1946. 1951 is actually the year when it kind of made it to our homes, literally, thanks to the commercial rollout going from 49 in terms of the patents. Anyway, so that's how it all started. But what I wanted to point out in this slide, going beyond the chronology, is that in order to produce PTFE, one needs to use PFAS, right? And this is where things could go wrong, because that's obviously a huge problem. Because whereas Teflon is safe enough, we all agree that Teflon might be safe as Teflon itself. That's how it dodges the regulatory bullets. But as we saw a couple of slides back, a polymer can degrade. And how can Teflon degrade? Teflon can be burnt, overburnt to create PFAS chemicals. So when you heat your pan for too long or leave it overheated, that creates PFAS, right? So if the pans are overheated or chipped, PFAS can leach from the nonstick coating into your food. And this is why arguably there is a real need to go for PFAS-free alternatives, right? Okay, that's a good bit of alarm ringing. So now, how is research responding? Let's look at the good sides of the sites where we could come in and change things. By we, I mean scientists and engineers. How can it's of course the onus is upon us to change things for the future and for the present. And if we look at the existing viable treatment solutions on your screen, there are separation processes which are still relying upon age-old materials mostly, such as the state-of-the-art right now is activated carbon. Mostly the granulator activated carbons or the powder activated carbons, two forms of it. Then there are ion exchange resins, membrane processes, and there are new generation adsorbents that someone like myself and my team is looking at. They have some drawbacks. The most important, the most infamous ones being competitive adsorption. Operational expenses can be massive because to recycle adsorbents, that's not easy. And the kinetics of something like an activated carbon can be really sluggish. So residual PFAS enriched concentrate or adsorbent, that is a major drawback that all of these kind of grapple with. Destructive processes. This is including ultrasonic cavitation. Again, there are others, but the common drawback in all of these are energy intensive processes. You are gonna, each of these work as proof of concepts, but are they viable to upscale for bulk purification? Well, not really, because each of these processes can have high energy footprint. So that means that, and also can consume hydrofluoric acid to sometimes come up with the precursors. This won't really allow for a greener and viable alternative to mitigate the PFAS problem. Now, this is the state of the art. Like I said, GAC and PSE, granular activated carbon and powder activated carbon, but look at the scale there. We are dealing with this scale over here, and we are trying to have an efficient, by efficient, I mean cost efficient and energy efficient. Right now, we are struggling with cutting down on the capital expenditure, the operational expenditures, and the concentrate disposal. That's also a big elephant in the room which needs to be addressed, because concentrate, once the PFAS pollutants are concentrated, we can't just throw them out. There is no dumping ground for this. So that they have to be, even if you burn them down, it doesn't really go. So all of these things kind of make sure that it's a complex set of problems we have here with the state of the art right now. So the treatment technologies right now, primary considerations, I would like to give you a overview of what are the aspects that matter in terms of what are the boxes that need to be ticked when we are trying to come up with an alternative treatment solution. Space is a big thing, because not just because the amount consumed, but also this is highly toxic substances when you concentrate them in one place. So we have to make sure this space is compatible to kind of store and to contain all the toxicity. And then the pre-treatment requirements, removal effectiveness, of course, like that's the most important bit in a way, because unless you have good enough adsorption, good enough capture capability of the material itself, it won't really fly. Of course, the second bit is how much each process will need to invest into. Because as we learned a couple of slides back, it can't be retrofitted potentially to existing process design, because every process design might be fraught with inappropriate gaskets and whatnot. All these little bits and pieces of things that we use on a day-to-day basis in the lab have PFAS in them. So there is no way we could just change one little thing and solve it. So operational expenses is huge. That's the truth. So be that as it may, it is what it is. Disposal of waste and media and changing the whole thing bottom up is going to be having a massive implication in terms of the cost component. Now, what my team is doing and my area has looked at in this regard is follow this approach. What do? We look at water stable, low cost, solid sorbents, which offer the right chemistry for PFAS capture. What do I mean by right chemistry? Because I would like to think myself as a materials chemist who come up with materials that are relevant to sustainability, that are relevant to cleaning air, cleaning water. So this is what my group is focused at. And in our group, what we do is we come up with this functionalized framework solids, which looks like something like that, which has pores and which has surfaces to offer. And those surfaces, if functionalized right, with the right pore chemistry, with the right pore size, they can leverage strong physisorption and or weak chemisorption. So this means I'm not sure I can cover all these technicalities of these words, but in simple terms, I want to bind to the strongly to my PFAS toxic molecules, PFAS contaminant molecules, using either of these modalities, either physisorption or chemisorption. And to do so, I'm using the charge on the surfaces. So this is, yes, it is indeed these kind of surface chemistry for these porous materials can indeed lead the charge against PFAS with or without optimal porosity. The reason I emphasize on the porosity bit is we have got ample amount of data at this point in time, which proves that porosity might not be the most essential prerequisite to enable water decontamination. So over the years, or rather decades, porosity is touted to be a game changer in terms of capturing molecules like PFAS, because what pores do, they kind of immobilize, they encapsulate, or they absorb very efficiently guests like PFAS molecules. But in a kind of counterintuitive approach in this case, we have found that even if you have the right surface chemistry on a transient porous or a non-porous solid like this, schematically expressed here, it could lead to the right surface chemistry, right optimal porosity might not be needed, but what you want is an optimal hydrophobicity and optimal surface chemistry that makes sure that the sulfonates and the carboxylates, those charges, are having the right interactions to come and spend more, to get captured, like we have here in this case. So yes, these are the key takeaways from our recent result from our group, and which says a lot about which we learned a lot from in terms of how to design PFAS removing sorbents. So just before I go out of my own work, so one thing to point out is the regeneration cycles, because you need to have multiple recycling of this kind of a sorbent, and this is how the process could get advantage from the recycled recycling number. Unless it's recycled, there is no way such a high cost sorbent could be viable. These things can be high cost at the first go. Yes, there is a initial investment into making such a niche sorbent to begin with, because when I'm competing with something like a carbon, right? Carbon is dirt cheap. So this is where things can go difficult when you are just focused at minimizing the initial cost of the precursors. There is a big vision to it, because if you have multiple regeneration cycles, you are going to save it over the long run. Okay. Then there are policymaking, which, well, there is no one size fits all. The reason I say that loud and clear is there has been sometimes policymakers have talked a lot about how we should have substance by substance risk assessment in PFAS, and because of the evolving definition landscape that we just covered a couple of slides back, it's impossible. For something like 10,000 chemicals, we hardly know what these chemicals can do. So management of these chemicals on a specific chemical to chemical basis, it's a challenge of an order unknown to us. So we can't perhaps deal at the moment with specific case like chemical specific assessment and management. So rather, the best approach potentially could be to move away from it altogether. And as I said, to adopt a safe and circular by design approach, right? And this will definitely limit the future pollution. So policymakers could potentially adopt something like the Minnesota rule right now. This was the state in this which was the worst affected because they had the biggest factory for 3M. Anyway, the Amara's law in Minnesota right now takes effect in stages between 25 and 32. And well, it does take into cognizance all the things that we covered. And yeah, what we can do on a personal level. This is, I find it very relevant as a layperson. If I were not a scientist and I would be given this talk, I'd be seeing what I'm seeing today. This would be the changes I would immediately make to my day-to-day life. Try to avoid these few things. I'm not advocating anything in particular, but try to minimize your interactions with these things as much as you can, and try to read the labels, perhaps, because what we could do as laypersons is not to just think that everything that comes from a big company, big corporate is safe. So just read into the fine print, read into labels and figure out if it has a label for fluoro, label for PTFE. If there is, yeah, take everything with a pinch of salt in today's day. Anyway, that's a good practice, I suppose. Okay, so with alarm bells ringing, literally, for public health catastrophe, as we all saw, I reckon it is time we take this matter seriously. And even on a personal level, as I just covered, the way tangible policies and actions have been sluggish at the governmental level, it might indeed take like an angry Hulk to wake Brussels up in the form of Mark Ruffalo in Dark Waters, that movie. So with that, I do hope that you won't remember this bit of talk, from me solely for its gloom and gloom, and rather on an optimistic note, we should recognize that it is high time we find more efficient solutions to this PFAS predicament. And yep, I'll be delighted to take up questions. We'll now leave the floor open to discussions.
Perfect, Soumya, thank you very much. I'm sure I speak on behalf of everyone on the call and say it was super, super informative, and thank you for even taking the time to pull it all together and taking us through that journey. Just for everyone on the call, I'm aware that there's a security policies conflict which might be stopping people from posting in the chat and Q&A. So I have enabled microphones and I have enabled cameras for everybody. So if anyone would like to come in and ask a question or start a discussion on a topic, please feel free to just raise your hand, turn on your camera, and introduce yourself. I might actually start the ball rolling as well, just on questions, Soumya. So can I just check with you as well? your perspective on kind of future for life sciences in particular. So obviously the life sciences sector is somewhat outside of the fine chemical sector, but heavily reliant on the fine chemical sector. So we face a very big challenge in terms of ensuring the medicines for the generations of today and future generations, and ensuring their availability and the robustness of supply, looking back towards COVID and other challenges that the sector has faced over the last, say, decade or so, which, you know, has definitely tested the resilience of supply chains, and the future looks even more turbulent. But if you had one message kind of for biopharma chem, shall we say, and medicine manufacturers to do with PFAS and forever chemicals, what would it be?
Well, I mean,
not to put you on the spot.
No, it's a very good question, I suppose. I mean, because there is no easy solution to this. We all understand, in the sense that the scale we are dealing with is not just the numbers we saw today. I'm talking about this is not going to be a retrofit, right? This has to be getting away from what have we completely ripping off the existing processes and validating new things in the biopharmachem sector will be the most important thing to do. But I understand that there needs to be time gone into this. It can't just happen immediately. But it needs to happen. The strategies need to be put into, like, actioned upon now and no later. Because unless we strategize it first, it won't roll out the way we'd want this to happen. This is not a cursory attempt of, saving our faces. This is going to be a massive change in terms of how the process design can happen. If that does make sense.
It does, definitely. And just out of curiosity as well, and maybe you're aware or not aware of this, and if you're not, it's okay. But I presume there is probably a new frontier of medicine to remove PFAS, or say of therapeutics anyway, or medical devices to remove PFAS from the body also, because as you mentioned earlier, there's no established half-life or elimination criteria for these compounds once they enter the human body.
That's a very good question. I really like that, but there is not enough data that allows me to comment much in more details, because the only chemical that has been studied very well in terms of what you asked is PFOA, because that was detected as a thing from the early 2000s, and then came along PFOS, and then came other stuff, and now we have run ourselves into so many other alternatives that it's so tough to kind of navigate this any further. But the point I'm trying to make there is we don't know. We really don't know those critical numbers that you would like to know. In other cases where you are dealing with 1 or 2 or 3 chemicals, it's really perfectly normal for people to determine those parameters. But for PFAS, you can look it up yourself and you will struggle with many different PFASs throwing up with unreliable, irreproducible sets of data. This also stems from the intrinsic challenge in analytics, by the way. I should point that out, that for other analytical techniques, such as, an undergrad lab perhaps would have a UV detector, which might be good enough for detecting a normal water pollutant like arsenate and so on. But with these, we need a top of the line LCMS with a quadrupole detector. And without that, we are not knowing the numbers with accuracy and precision. And this is what has also caused the paucity of data. There's a reason why there are so less data, and I'm sure people are motivated to study them, but the problem is not enough resources are out there to study these with the right amount of accuracy and precision that one needs.
Perfect. No, I appreciate that, and I can completely understand that. And I think it does, I suppose, for the benefit of everybody on the call as well, open a new frontier, I suppose, or a new future challenge for our sector. Is, if you look towards sustainability and where we sit at the moment, I did mention at the start, sustainability, we're retrofitting sustainability onto existing processes. And look, we're doing a great job there, and that work has to be done as well for the benefit of the planet and for the benefit of future populations to come. Decarbonisation, lowering energy, kind of optimizing supply chains, optimizing material usage and efficiencies within processes. That's 100% the here and now, and the activity that does need to be delivered in the short term. But I do think, as you mentioned earlier, I do think you made a great point. We need to also consider starting from the bottom up again and looking beyond those activities and into our processes themselves, and understanding end to end where our raw materials come from and where all of our products or byproducts or outputs from each one of our processes and each one of our products end up back in the environment, and what does that look like? It's not an easy challenge. It's definitely it's not straightforward.
Just to add into that mix is the fact that the European Medicines Agency and the ECHA will have their own will have their own guidelines getting rolled out very soon, I suppose, considering the EPA has updated theirs. There has been a recent update already in the ECHA website, the European Chemical Safety Guidelines website, that there is about to be a change to the levels, the MCL levels that we have. So long story short, we will soon face this crisis when none of the biopharma chem or the pharma industry compliance numbers will look the same as before. So we need to adapt, and that needs to happen quick. That's the need of the hour. There is no other way to put it.
I think that's a good point, a good message to leave it on as well. The change is coming, the change is inevitable, and we need to try and get ahead of this. So I'm just conscious, if there's any questions from anybody else, the chat is there, or please feel free to come in and introduce yourself. If not, we'll give people time to go grab a cup of coffee.
We can have one-on-one conversations also, like if someone would like to just turn on their microphone or camera.
No, all good for today. Right. We'll leave it there, folks. And you have our email addresses, different things. So
please feel free to get in touch with me. You have my email address, I hope. So we'll look forward to getting this upwards and onwards, and not to be doomed by this gloomy stuff that we saw today. All right. Thanks, everyone. Take care.